Thanks very much. I like a nice, concise introduction. Hopefully the talk will be as concise. I'm slightly worried about pushing my time limit. But I'd like to talk to you about implicit, explicit, or IMEX multi-step methods for fast wave, slow wave problems. And the qualification on fast wave, slow wave problems is important. IMEX methods for convection diffusion problems have different optimal choices. So we're going to explore the perhaps slightly less known fast wave, slow wave problem. And we're going to split up the PDE so that we have a vector L that is a linear operator that's going to be used for the processes that need to be modeled implicitly on short, because they occur on short time scales. F of u is the explicit part of the PDE, and u is just the vector of unknowns. So an IMEX multi-step approximation takes this following general form where q sub n approximates our unknown vector at time n delta t, and then the pair of coefficients alpha and beta, they define the explicit method. Notice our index on the coefficients doesn't run all the way up to time n plus 1 in this term, so this is the explicit part, and alpha and nu define the implicit part of our scheme. So if we think about a simple IMEX method, the most famous and simplest one is trapezoidal over 2 delta t for the implicit part, something we've used in atmospheric science for some time, and an explicit leapfrog scheme. And if we look at how this behaves in a simple test problem, similar to what we heard about yesterday from Sarah Jane, we're going to have an ODE, so we've suddenly lost our PDE. We'll have an ODE with a low frequency forcing and a high frequency forcing, and so Q is some complex valued unknown. And we're going to go ahead and make the identification that would be important in later applications, where the linear part, the LQ, is going to be the high frequency forcing, and this other part, which is actually still linear in this obviously very simple case, is a typo here, low frequency forcing. Okay, so if we look at the amplification factor associated with these solutions to this ODE, what we can do is plot the amplification factor in a contour plot where we have the low frequency forcing along the bottom and the high frequency forcing along the top, and it's, in this case, it's symmetric about this, this axis, so we're not going to bother to plot that part of the plot. And what we see here is that, ignore these things, they'll come up later, but the region of stability is something that extends outward and upward, and so small enough values of delta t, which are in this vicinity here, give you stability, which is certainly good. And in fact, this is a very nicely behaved IMEX scheme in the sense that two things occur. First of all, it's stable whenever the explicit part alone would be stable. This would be the explicit part in a more general problem. And all we have to do is ensure we pick a time step that keeps us stable on the omega h delta t equals 0 axis, and we're stable for any other larger value of delta t. So it doesn't matter how high frequency the high frequency forcing is. And the other thing that's nice about this is this stable region includes this wedge that has us being stable whenever the low frequency forcing is a certain factor less than the high frequency forcing. In this case, that factor is simply 1. That is, it means that whenever you've correctly identified the high and low frequency forcing, you're going to be stable anyway, no matter what else is going on. So it's a very nice behaved scheme in that sense. However, of course, it's no good at all, right? This scheme is never used because, as we all know, time splitting arises in leapfrog integrations of nonlinear problems. And also, there is a concern that the trapezoidal time average doesn't do enough damping of high frequency waves. It's neutral. So in fact, the trapezoidal part of that IMEX method is often changed too, so that it's forward biased to try to damp high frequencies. Okay, so what's more common in actual practice is this forward biasing of the trapezoidal implicit part over the 2 delta t step, and then something is done in the way of filtering, and we heard about this yesterday, the leapfrog scheme. You could have an Robert-Asselin filter, or Asselin filter, or you could use the new raw filter. And when I talk about the raw filter, I'm not going to talk about the second order choice, because I like this one better. But at any rate, this is one that has a region of stability that's fairly decent. And so that's what all this is about. If you're here yesterday, you're all up on it, except for the notational change, perhaps. So the weaknesses of all this, well, the raw filtered leapfrog or the RA leapfrog or whatever is first order unless we choose this one particular value of the raw filter. The computational mode in any case is only weakly damped. It limits the choice of spatial differences. It's not suitable for diffusion at all. You have to take your diffusion as a forward time step over 2 delta t. However, I will throw in the fact that, as we'll see if I have enough time to get to the numerical results, the raw filtering is definitely an improvement over the RA filter. So for those of you who still love the leapfrog scheme, I definitely suggest you use this one instead of that one. And the off-center trapezoidal method actually has its problems too. It's also reduced to first order. The damping is actually not very scale selective. And in one sense, one of the most unequivocal results, hoping I get through everything, is that this is just a really bad idea. Offsetting the trapezoidal method seems to just mess everything up. So let me show you the first example of how this happens. So if we look at the influence of the Robert-Asselin filter and off-centering, what I've got on this top plot is the very left panel is the one we saw before. There's no forward biasing of the trapezoidal scheme, that is the value of theta is 1/2, and there's no filtering of any type. So this is the plot we saw before. You can compare it to what happens when you still decline to do any filtering of the leapfrog, but you forward bias things a bit to do some damping in the trapezoidal scheme. In that case, what has happened is you have indeed got some damping for higher frequencies, which is one of your goals. But notice you've already lost one of the nice stability features that you had with the standard scheme, which is that now, so let me explain what's actually plotted here. Got a little ahead of myself. So the white regions are still the regions with the amplification factor less than 1. The little gray region has an amplification factor a bit bigger than 1, and I should have reviewed what it is, but I believe it is a value between 1.01 and 1. So it's a small amount of amplification, but of course repeated integrations with that kind of amplification will blow it up. And then bigger than 1.01 is the brown area. So we see what happens here is that in fact it's unstable for all values of delta t larger than 0 for certain regions very close to the origin, right? So we don't have this nice feature where you just pick things to be stable for your explicit part and your implicit part is stable, unless you take a relatively, you can get into that kind of region with a big enough omega delta t, omega h delta t, but for smaller values of omega h delta t, you're going to get into trouble. So that's a bit discouraging. And then if we turn on the Robert-Asselin filter, we'll look at the raw filter in a moment, what we see is that there's, in the case where things are centered in the implicit world, we retain this nice stability structure with respect to pick a time step that's stable for the low frequency explicit forcing, you'll be stable. But we have our wedges narrowed down a little bit. So we've lost a little bit of stability that way, but it's not too bad. However, if we once again try to forward bias the trapezoidal scheme to get this damping for high values of omega h, again we have a region coming down toward the origin here through which the scheme is unstable. Okay, so this is actually not working out so well. Now if we go to the, so there we go, centering spoils the trapezoidal stability in the limit of moving down this axis. We wind up with an unstable region. The raw filtering and off-centering gives us, well, the raw filtering and the off-centering does the following things. The raw filter business is on the bottom, just for comparison. The bottom two plots in the last picture are reproduced up here. So this is the Robert-Asselin filtering. They're both using this Asselin filtering coefficient of 0.2. And the raw filter, I picked 0.53. So what we see here is that when you use the raw filter and do not off-center the trapezoidal difference, you're in pretty good shape, but you have lost some stability. You have lost some range of stability. You have to use a smaller delta t, but things work out okay, subject to that smaller delta t. However, again, if you forward bias the trapezoidal difference, you get into trouble for small values of omega h delta t. Yes?
Just a clarification here, what you call trapezoidal is the semi-implicit.
Yes, let's just go back here. Okay. It's this. So when I say theta equals 1/2, that would be the trapezoidal or Crank-Lewis, whatever you want to call it, over 2 delta t. And as soon as we choose theta bigger than 1/2, we've got it forward biased and we get some damping.
So does the light grey area kind of basically leap down to 0 as soon as theta's a little bit more than 0.5? Because you've
Yes.
got quite a big point
Yes.
theta there.
Yes.
So theta 0.501 is already...
There's already a little piece coming down.
Wow.
Right. And we'll see in the numerical results, assuming we'll get there, otherwise I'll throw them up in the discussion in the afternoon, that you can really see a number of bad behaviors associated with doing this in some of the test problems. Okay, so we're not completely happy with our results here, and we ask, can we do better? And what we're going to do is search around for better results. We'll limit ourselves to multi-step schemes simply for tractability. I'm not claiming the Runge-Kutta world might not be even a better place to look. And we're also going to, in practice, of course, people have looked at multi-step methods for solving ODEs forever. And so people have thought a lot about this. The literature is amazingly deep, and I'm sure we're not as far into it as we should be. But we're going to build on other people's shoulders. We're going to try generalized Adams methods and generalized backwards methods to get our IMEX schemes. So let's first start again with obvious possibilities. One is to use the regular trapezoidal method. Why bother doing it over 2 delta t? And this is it's astable, and it's the optimal 2-step implicit Adams methods. All Adams methods involve this kind of approximation of the time difference and then other stuff on the right-hand side. So it's optimal. It's very accurate 2-step method. Seems like a good choice. And then to avoid the amplification of oscillatory solutions, we'll jump beyond the second-order Adams-Bashforth method to the optimal 3-step Adams-Bashforth, or explicit Adams method, which is the 33-step Adams-Bashforth method. It treats oscillatory solutions very well. This combination is used extensively in IMEX schemes for convection diffusion. Also seems like a good choice in that sense. And then while we're at it, we'll look at the other optimal choice, from the other obvious choice from the other family. The backwards family, we use the second-order backwards difference, another standard method. This is our backwards difference in time. And this is an L-stable method that's used in a lot of contexts. And then we'll use a, unfortunately, there's not quite as good a backwards method as you marry up with this, but for something that's been used in the past is this explicit backwards difference. So we replace the value at time n plus 1 in the true backwards difference with some forward extrapolation. This does amplify oscillatory solutions, which could be of some concern. If we look at the behavior, again in this fast wave, slow wave problem, same context we looked at previously. I'll explain these little red segments later. What we see is, first of all, this combination of the trapezoidal and third-order Adams-Bashforth method performs very poorly. It's completely useless, in fact. Even though it's a great method for convection diffusion, it's a complete loser. And this method is not very good either. It has the same problem with stability near the origin, and the wedge in which things are stable for larger time steps is relatively narrow. So it's not particularly attractive either. So neither method is really all that good. What next? Okay, so let's generalize to look at the whole Adams family. Those of you who are old enough know the Adams family is a funny group of people, but generalize to include all second-order methods using no more than 3 time levels. And also, we're going to limit our choice to methods that are stable along these little red line segments, both the red line segments. So that winds up doing a good job of catching obviously unsuitable methods. Notice all these instabilities that have been a problem have involved something that comes down toward the origin or involves some sort of impingement and narrowing of the stable region at the edges of this little pair of line segments. And this is going from omega L delta t equal a half up to omega h delta t equal half and back down if you wonder where those segments are. Okay, so here's the Adams family in mathematical form. All second-order implicit Adams methods can be expressed in this form using no more than our limited number of time levels. We're going with actually 2 time levels for the implicit part. And so it's astable, 3 time levels for the implicit part. So I said that 1, 2, 3. Astable for c greater than 0. So that's nice. So I didn't really talk about this, but we'd like our implicit method to be certainly astable, which means that nothing's going to get out of hand no matter how big the time step, although we might actually like some damping at infinity for high frequency modes, which would require something more than simple. Well, I'm not really talking about that in detail. It's astable, and The trapezoidal method is the one you get for c equals 0. We don't have to use this level, which it would be otherwise nice, except it doesn't work too well. There's another classical method introduced in 1978 called AM2 star in somewhat more recent literature, though it's not widely used anywhere. And c is a half, so that knocks this term out. This is an optimal method with respect to accuracy for a test problem that looks like, well, a test problem with a bit of time dependence in it. Let's just leave it at that. And then the second order explicit Adams methods can be written in this form. B equals 0 gives you the second order Adams-Bashforth, which gets rid of this last term. B equals 5, 6 is the third order Adams-Bashforth. So we have a family of methods, depending on our choice of C and B, that we could try to marry together to make Adams IMEX methods. There's a backward family as well. And the backward family looks like this. It's astable for c greater than 1/4, where c is our parameter. The BDF2 case is c equals 0, knocking off that term and that term. And the second order explicit backwards methods would take this general form. The third order one, there's a third order one available when you choose b equal 2/3 that has been used in various contexts as well. So we have these general Adams and backwards methods with a free parameter in the implicit part and a free parameter in the backwards part. And if we now demand stability over this whole red line segment region, it turns out the result is somewhat astonishing. You get stability along the red line segments for the Adams family when c is equal to 3b plus 1 for c in this range. This, I'm sorry to be at the Newton Institute here, where we're all mathematicians, and say we didn't really prove this. Although the integer nature of it makes me think there is a proof out there if somebody's clever enough to pursue it. What we did do is an extensive numerical search, and if you change this intercept just slightly, say 1.01 or 0.99, you don't get any stability at all along the whole red line segment. You get one of these little funny regions of instability coming down and touching the origin.
So the claim is that that's necessary and sufficient. So it works both ways.
Yeah, all those values work, and it does appear to be. Yeah, certainly it's sufficient. But we're claiming, well. So I'm not exactly. I'm sort of admitting I haven't proved that it's necessary, right? But the hypothesis is that it's necessary.
Is there something special about that red line?
We didn't actually check that. We could have moved the line a little bit. I don't think that would matter. And the backward family also comes out to give you a nice relationship. Again, that looks like it involves integers, at least to 2 decimal places. And it has a region of this single parameter C of stability as well. So we can pick members of this. We can pick pairs from the explicit and implicit methods using this relationship for both, or this relationship, depending on whether we're working with the Adams or the backward family. So yeah, there's a hypothesis out there that there's got to be a way to prove, if this is really as simple as it is, there ought to be a way to prove it. But we haven't done it. Okay, so now let's look at what we get. Let's go back here for a moment. So now we've got a free parameter. What should we do? Well, one obvious choice is to pick those 2 third-order explicit methods, right? That will give us our maximum accuracy in the explicit part. And there's only one explicit choice available in each family. So that's one obvious thing to do. So if we look at the amplification factors associated with third-order explicit methods, this combination here is the Adams family and the third-order member. And the third-order explicit piece is that third-order Adams-Bashforth method. And this actually works out quite nicely in the sense that we recover some of the features we like to see. In particular, if you pick a stable value of delta t for the third-order Adams-Bashforth integration of the explicit part, you can let your omega h be as high as you want, and you have stability. So that's a nice thing. The width of this wedge is a little narrower than the leapfrog scheme, but it's still pretty wide relative to the other methods. So this is, in most respects, a very attractive choice. And I'll get to the respect in which it has a bit of a weakness, which is strictly computational in a minute. This second case, using the third order backward explicit difference, also works pretty well, but the wedge business doesn't expand as nicely. But you've got a pretty good region again where it's almost true. You just make it stable with respect to omega L delta t, and everything will be okay. So that was that. And now let's go back again. Well, this is not really that helpful. I didn't really need to go back. Conceptually, let's ask what can we do besides using highly accurate explicit methods. The other thing we might want to do is essentially use the best implicit part possible. And that's slightly fuzzier, but basically the best implicit part involves using the classical second order backwards difference, which has is an L-stable method with a lot of good properties, or this AM2 star that is in some sense the most accurate member of the Adams family involving these 3 time levels in second order accuracy. And if you look at those two methods, you again get reasonable behavior. You've got almost a situation where omega L delta T determines stability. Not quite the case here, but close. Your wedge is getting tighter as you move along. But these are actually also useful members, as we'll explain if we look at the test results. So if we look at this and compare these two plots to the two we just looked at, a negative is that in both cases, nevertheless, the stability regions are smaller than for the third order explicit schemes. But the positive is that the condition numbers associated with the implicit parts for these methods are better than the implicit parts for the previous methods, which I had named AI2 star and BI2 star. So we in typical problems seem to get better condition numbers, which will be good for iterative solvers using these approaches. Okay, so there's a test problem going to come up that I hope to flash up. But the condition numbers in a test problem where you are treating pressure gradient and divergence terms as the fast stuff, that's what propagates the acoustic modes, wind up having in a form where this leading factor multiplies this thing, which depends on grid spacing, speed of sound, delta t. So you can compare all the condition numbers just by looking in this table, and you see the lowest condition number is this BDF2. So if you're trying to do some iterative solutions in a problem that is complex and requires iterative solutions, you're going to be happy to have the smallest condition number. In this case, your condition number is somewhat bigger, in this case with AI2 star, which was, in other respects, the best choice. This is the one that pairs with the third order Adams-Bashforth method to give you a very nice solution to that fast wave, slow wave problem, but it does have the largest condition number of the bunch. Our old leapfrog scheme, without forward weighting, the trapezoidal time difference has a condition number of 1 in this context, which is kind of cute. But in any case, you can see as you move down here, the two implicit methods we identified have the two lowest condition numbers. We move up to some of the others and we get somewhat higher condition numbers. So I've got 5 minutes and I can probably just squeak in. So I just blast on through, or should we stop for questions and talk about the numerical results this afternoon? Blast on. Okay. So we have also an analysis of a linearized system that supports sound waves and gravity waves. I'm skipping over all of that. I want to talk about some numerical simulations with a fixed spatial discretization to explore convergence in time to a compressible solution to a gravity wave problem, computed with very small delta t. There's your fourth order Runge-Kutto method was used to compute the solution. And so actually, I think I'm just going to show the picture. Skip over that. So what we've got here are two cases, one of which is non-hydrostatic, so the x dimension is different than the z dimension is the same in both of these. We have some non-divergent forcing that's pulsing that is producing acoustic waves and gravity waves. We have rigid boundaries, top and bottom, periodic on the sides, and we've stopped this before the solution is wrapped around significantly. So what I've contoured here is the x velocity, and these little shaded regions show you where their source region is. So the source region generating the non-hydrostatic waves looks like this, and the source region for the hydrostatic waves looks like that one. And we wind up with disturbances that propagate out. And this, should you go to our paper, you'll discover this figure does not match our paper due to the extensive work of Hillary and Sarah Jane and others. We've discovered that I made a mistake and lost the right figure. So anyway, we'll post this in a corrigendum and I'll put it on my website. Should you want, for some reason, this figure, don't go to the paper. But anyway, it's freshly unearthed and inserted in today's talk. So this is, we're going to look at the error, the RMS error, as we decrease delta t repeatedly using various methods for both of these problems, starting with the non-hydrostatic case, which in some ways, for a small scale people anyway, is the one of more intrinsic interest as we push down to small spatial scales and want to be able to deal with convection. So what we've got here, and This is a figure that somehow is not amenable to changing colors in Adobe Illustrator. So I'm stuck with the black and white version. It's complicated. But there's some very interesting things on here. Let me give you the bigger picture, and then we'll start to list things to watch for. This left-hand side has basically the previously identified methods, which are these leapfrog schemes with or without forward centering the trapezoidal part, and with or without the Aslan filter or the raw filter. That's what these first three are. This is the BDF2 and an explicit piece also. Then you see there are symbols and there are lines. The lines are the cases where we've treated buoyancy implicitly. Let's start with these. The symbols are where we did buoyancy explicitly, which means all we did implicitly is pressure gradient and divergence, just the acoustic modes. But we can throw the buoyancy into the implicit part pretty cheaply if you want to. So that's the case with the lines. And then over on the right-hand side, we have these four methods that I introduced as attractive members of the atoms and the backwards family. And again, the same business occurs. The symbols are for buoyancy explicit. The lines are for buoyancy implicit. OK, so now let's look at this. And I think I'm going to switch to the next one where they're slightly smaller, but we have something to grab onto here. The first thing, I want to reinforce this idea that forward biasing the leapfrog scheme just is not a good idea. Okay, so first let's look in the old context at this black line and the diamonds. So this is the leapfrog scheme with a little bit of Aslan filtering, but no raw filter. So there's just the Aslan filter, and it's forward biased at 0.06. And if you compare the performance when you're only doing acoustic modes, that would be the diamonds, with what happens when you throw the buoyancy in, you see this fact that you've degraded the order of accuracy and somehow degraded your whole accuracy substantially by starting to treat the buoyancy with this forward bias implicitness. We lost a lot of accuracy, right? You compare this black line with these dashes. All that's happened is we've used the same scheme to either include the gravity wave forcing through buoyancy or not. And we lost substantial accuracy and we did it implicitly. When we do just the pressure gradient and divergence terms implicitly, however, we are able to capture the same thing we get with the standard leapfrog scheme. And it doesn't care in the least, these little boxes and the gray lines lie right on top of each other. It doesn't care whether you treat the buoyancy implicitly or explicitly. It's only when you forward bias stuff and pay that accuracy penalty that you got into trouble. Also in here we have these, the long dashed line, the pluses are the second order BDF2 scheme, and you can see it's matching. So what the heck is plotted here? Sorry, this is relative air and buoyancy in an RMS sense, and this is the CFL number, and they're both on log scales, so watch out for that later. But you can see, and they terminate at the maximum stable time steps. They terminate for CFL numbers around 0.7, 0.8. Finally, and so this is what Paul was happy about yesterday, is if you look at the raw filter version, which is these X's and dot dash lines, it's actually producing less air than any of the other leapfrog trapezoidal flavors. So it's doing better. You pay, and also you're able to pay, essentially take as big a time step too, or maybe even slightly bigger in this particular case compared to this Aslan filter. And we ran these things out. We empirically determined the stability limit by running it out a long, long ways for a lot of time steps. And they more or less match what we expected theoretically, but this is an empirical result where these lines cut off. Okay, now we go over to this case. And what we see here is that if you treat only the sound wave acoustic part implicitly and do your third order accurate solution with either this third order Adams-Bashforth method or the third order backward method, you get very nice results. Low error, even at coarse time step, and of course, well, not of course, and somewhat surprisingly, the convergence appears to be third order, suggesting again that the second order treatment in the implicit part of the pressure gradient and divergence terms is not actually interfering with accuracy of your solution, at least at this time resolution. And then there's somewhat slightly less attractive behavior, but second order nevertheless for the other schemes. Okay. So the last result, let's go to the hydrostatic case. So the hydrostatic case now is one where the wave propagation is much faster in the horizontal, and so these are there's actually horizontal wind speed in this problem, right? In fact, I maybe should have mentioned it's a shear flow with variable shear to make it somewhat robust in terms of what it's testing. These things plotted on the bottom are CFL condition numbers with respect to advection, which would be the only limiting CFL condition if buoyancy is done on the implicitly. And sure enough, that's the case. You're able to take steps close to CFLs of 1 for the methods in general that are plotted as curves, because that's where we're treating the buoyancy implicitly. We treat the buoyancy explicitly. Now, because these waves are propagating quite fast compared to the flow speed, we have to take a much smaller time step. So watching that log scale, you can see we're stuck at CFL numbers down less than 0.2 if you want to do the buoyancy explicitly, because the waves are going so fast. Basically, you have to pay attention to your fast-moving wave. But anyway, the overall picture is similar, except that the trade-off between the new methods and the old methods is less clear-cut in the sense that the raw filter is doing pretty good, right? So here's this raw filter, again at my preferred stable value, 0.53, and that's the x dot dash line coming. Oh wait, yeah, the dot dash line and the x's. That's this one coming up here. So the actual errors in time step at coarse resolution are similar to what you get over here. So it basically does as well. But of course, since these are our higher order methods, as you start decreasing the time step, it behaves a little better. So, coming to the summary, the new IMEX methods with third order explicit step have higher accuracy than the leapfrog trapezoidal. They have better stability. The computational modes are very strongly damped. So, people whose experience with computational modes revolves only around the leapfrog scheme need to rethink, because most of these better multi-step methods have very strongly damped computational modes that just die off. They never grow up. They never get big and strong. Okay, so diffusion is also easy to handle in these contexts because these methods will have a robust region of absolute stability that's not just the imaginary axis in some sense, if that makes sense to you. And they also actually have more scale selective computational damping than this traditional combination. Okay, and they can be minimal cost relative to the leapfrog trapezoidal scheme in the non-hydrostatic case. So if you're really trying to do clouds and are down at that grid resolution, these are very attractive methods. In the case of the hydrostatic test problem, the most efficient choices are those with the best implicit part. So we switch from using the third order explicit methods to the best implicit second order methods. But the superiority over the leapfrog trapezoidal method is less pronounced, particularly when you use the raw filter. So it's almost a wash in that, except for issues like diffusion. So that's it.
We will have a discussion session this afternoon on the 3 talks, but we should maybe, if there's one quick question.
Quickly. So Dale, the BI 2-star BX3, is that just the implicit BDF with a third order extrapolation?
No. Oh, you mean what is BX3 star
BX3.
or what is both of them?
Well, okay, let's go. BX3 star is just is that the third order
You've
extrapolation?
used BX3 star.
Okay.
So if that's what it's just one of those ones that gets you to third order. Yeah, for the
And the BI 2-star?
BI2 star is not BDF2.
It's not
different.
BDF2,
It's not
something else.
It's the one that's compatible via that. So we go for the third order scheme, then we pick the one that's compatible via that relationship, the linear relationship.
Okay.
Go on then.
Very quickly, if you go back one slide, Dale, in the dot dash curve, oh sorry, one more.
We're getting there. There you go.
There's a kink in the dot dash curve, which I understand, but in the previous slide, there was a kink also, which sort of kinked the other way, if you know what I mean. Do you understand why those curves bend in that way?
Well, I haven't really thought much about it, to tell you the truth, but presumably they relate to.
Well, you said it's first order now.
It's degrading to
Yeah,
After
it's
the
degrading to
0.53
first order,
is
right.
first order.
Yeah, so this is degrading back to first order, which it has to as delta t gets smaller.
And on the next slide, it's
So we maybe didn't ever get small enough, right?
Right.
That's probably the story, because this is going to have to go back to first order as well as it gets small. I don't know exactly. This kink here is way out at pretty coarse resolution, so I don't think the order of accuracy tells us much at that kind of coarse resolution.
I'll have to save my question for this afternoon. Now time for Frank to talk on